So we are back at it, more recursion, more practice, and more method tracing. As always, starting off with some review questions. Do recursive methods need a stopping case in order to function correctly? Pause the video, come back. What's the answer? Absolutely, recursive methods need a stopping case. Otherwise, they will go on, in theory, indefinitely. Of course, they will ultimately cause a Stack Overflow error after running maybe 8 or 9 or 10,000 methods that open up on the actual stack. But yes, they do need a stopping case. Are recursive methods usually slower than their iterative counterparts? Pause the video, think about that. What's the answer? The answer is no, they're not usually slower. There are exceptions. We saw Fibonacci previously. There are other exceptions, but in general, a recursive algorithm will have similar running times and similar speeds with a big O analysis to their iterative counterparts. Third question, do recursive algorithms use more memory than their iterative counterparts? Pause the video. What is the answer? The answer is absolutely. So even if we avoid the redundant calls and those overlapping subproblems that we saw with Fibonacci, and you'll see with other examples, even if that's avoided, and in the best case scenario of memory usage, recursive algorithms absolutely use more memory, if by nothing else than the virtue that each recursive call is a new method that is opening up on the stack of methods, as opposed to iteration, which is just a single loop making that happen. So recursive methods do use more memory, but what is the value still? So why do we still use them? Because of their clarity and the high value with the software engineering. So what is recursion? The reminder, from the programming perspective, we gave this definition, solving a large problem by reducing it to a smaller problem of the same type. And again, recursion is a method that will actually invoke itself again and again and again, really splitting itself into smaller versions of that same problem until it arrives at a terminating condition, that stopping case. So this recursive method will have some sort of calls and conditional statements to check. Have we arrived at the terminating condition? If so, stop the recursion. Otherwise, let's keep recursing. So we're going to discuss this general structure of our recursive methods. We've seen that when we have this large problem, we want to break it down into smaller versions of itself, right? We had that factorial example. We utilized the fact, horrible choice of words, no pun intended, that n factorial is n times n minus 1 factorial. So n minus 1 factorial was in fact a smaller version of that original problem, n factorial. So 9 factorial is a smaller version of 10 factorial. So eventually we keep breaking this down into smaller and smaller versions of itself until that final smallest problem we actually know the answer to, and we directly return that answer if we're actually computing a recursive method that calculates something. If the recursive method is not calculating something, we'll just simply complete whatever task we're doing. So with this in mind, now we come to the general structure of our recursive methods. We're going to either break the problem down further into its smaller subproblems, or we've reached that final terminating case and we can now solve that problem. Of course, we approach this with an if-else statement in programming, and we now come up with 2 overall constructs for our recursive methods. Construct 1, if we have arrived at the terminating action, do that final action. Return that 0 factorial is 1. Return that thing. Otherwise, take one step closer to that terminating condition. Call the method recursively. Which methods would usually use this construct? Ones that are calculating something, that are computing some value and ultimately return that value. The second construct, if we have not arrived at a terminating condition, simply take one step closer. Nothing needs to get returned here. This is for usually void recursive methods that are not actually returning a value. So let's see these constructs in action. Our example using construct 1, we have this method we want to make called sum integers. This method will take in one positive integer parameter, n, and it will return the sum of all integers from 1 up until and including n. So this recursive method will sum all of these values up and then return that. How do we do this recursively? As we mentioned, this is the hardest part. This recursive thinking, this strategy, how do you convert an iterative problem into a recursive one? Because this would be easy to solve with a for loop. Just loop from 1 all the way up to including n, add each value of I to your sum, right? Super easy. Well, we're going to ultimately say that this is also super easy with recursion once we get practice. And it's important to give a reminder here. We would never want to really solve this problem with recursion. Why are we practicing this problem with recursion? Because we want to practice easy problems with recursion. We want to get comfortable with recursion. So then once we get to problems that almost require recursion and we need to use recursion to solve that problem, we want to be comfortable on those harder ones once we get there, right? So we need to solve this problem in such a way that the solution is a subproblem of the exact same nature, the exact same type as the original. That definition, solve a large problem by reducing it to a smaller version of that same form. So here's our method. Using n as the input, right? We want to sum numbers from 1 to n. We define the following function. We say that the sum numbers of n, it equals 1 plus 2 plus 3 all the way up to n. Hopefully that function is clear. Here's an example. Sum numbers of 7, it equals 1 plus 2 plus 3 all the way plus 5 plus 6 plus 7. So the question is simply, given this particular function, how do we make it recursive? And again, that's the hardest part, thinking recursively, that strategy. Because once we get that recursive thinking, the code is a joke. The code is so simple and straightforward once you have the recursive definition down. So the recap of our strategy from last time, given a problem, in this case the sum number problem, restate the problem in such a way that the large version is very clearly articulated. We pick just some random large number that we can plug into the problem. So maybe some numbers of 7, as we just saw. Now find a smaller version of that exact same problem. Just pick a smaller version. I say take a guess, but really make an intelligent guess. Just choose a slightly smaller version. Rewrite step 1 in terms of the smaller version that you came up with in step 2. Check to make sure that the smaller version is in fact part of the answer to the original. And if so, we just derived our recursive idea. Step 4, make sure you got a base case, a way to exit that recursion. Step 5, let's code it up. So using n as the input, here's our function. And remember, we want a problem, a method that will solve this exact same problem, but a smaller version. It needs to be recursive. So it should solve some numbers of n by reducing it to a smaller version, but of the same form, just like we saw with factorial. We're solving n factorial, but on the right side of this mathematical equation, this is not an assignment here, this is a mathematical equation, the right side is written in terms of the original. We have factorial here, we have factorial here, but this is a smaller version. This is what we're looking to do. So what's a smaller version of our function? So if we want some numbers of 7 to be our larger problem, what's a smaller version? Take a guess. Given some numbers of 7, we could say a smaller version is some numbers of 6. It's certainly the same form, the same type. It's some numbers, right? We're not expressing some numbers of 7 in terms of factorial. Some numbers of 7, we're saying, well, a smaller version would be some numbers of 6. The question is, can we use that smaller version as part of the answer to the original? So here's some numbers of 7, and we list out what that really means, 1 plus 2 plus all the way to plus 6 plus 7. And now we said some numbers of 6, it appears to be a candidate smaller version. I'm calling it a candidate because it may not be. We need to check it. It appears to be a smaller version. That may work, right? So it's only a possible smaller version. We need to check it. Can we use some numbers of 6 as a smaller version for some numbers of 7? Well, here's some numbers of 6, 1 plus 2 plus 3 plus 4 plus 5 plus 6. And now we want to check it. The answer is yes, we can. Some numbers of 7 is really 7 plus some numbers of 6. Just plug in what some numbers of 6 is. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6. And here's the 7 that goes to some numbers of 7. So here we can see that some numbers of 7, this entire mathematical equation is recursive. Why? Because to compute some numbers of 7, we're actually writing the right side of this equation in terms of the left, but it's a smaller version. This is the idea. So we can see here, this is the check that in fact, all of this, including this plus 7, that's some numbers of 7. But the final 6 numbers are really some numbers of 6. So the answer to some numbers of 7 does in fact contain some numbers of 6. So we've defined some numbers of 7 in terms of some numbers of 6. Similarly, we could say some numbers of 84 equals 84 plus the sum numbers of 83, leading us now to this general structure. Some numbers of n really equals n plus some numbers of n minus 1. What's left? What's step 4 now? Terminating condition. What is our base case? Base case, here's just another example. What is our base case? The base case is, we could say some numbers of 0 is 0. You could say some numbers of 1 is 1. You could say, well, the sum of the first 2 numbers is 3, right? But we said you really want to choose the smallest base case. So we're going to say some numbers of 0 is 0. That's our terminating condition once n is 0. So here's our final recursive definition. We say some numbers of n is 0 as long as n is 0. Otherwise, some numbers of n is really n plus the sum numbers of n minus 1. So check out, with that recursive definition clearly defined, that's the hardest part, that recursive thinking, that's really the code. We're going to say if n is 0, return 0, else return n plus some numbers of n minus 1. It really comes directly from the definition. So here's the code. Given n, what did we say? What is the sum numbers of n? Well, if n is 0, it's 0. Else, if n is not 0, what is the sum numbers of n? So think about the name of this method as being the left side of that mathematical equation. What is the sum numbers of n? We said it equaled n plus the sum numbers of n minus 1. That's it. That is some sexy code. That is some gorgeous code coming directly from the actual recursive definition. That's why this is so exciting. Recursion is fantastic. The clarity, the high quality software engineering is absolutely there. Now we're going to practice something called drawing the boxes. A skill we saw previously with iteration, and a very important skill, is the ability to look at our code and trace through that code and ultimately come up with what the output should be. Well, recursion, we need to practice that skill, but now it's a little bit different. It's not as easy to just see a loop and say what happens. So I call this drawing the boxes. So coding up that recursion is important, but another skill equally, if not more important, is being able to trace through that recursion. We're going to do this a couple of times, both here in the sum numbers problems as well on the following problem. So starting with sum numbers of n, we want to draw up the boxes, and you'll see what I mean by this. We're going to trace through the entire recursion. So tracing the sum numbers of 5, here's our main method that is opened up on the stack. It's currently the only method open on the stack. And we say int result equals sum numbers of 5, and then we're going to print the actual result. So what happens here inside this main method? We see here on the very first line of code, we call sum numbers of 5. So now main is on pause, and program control comes to this method that opened up on the stack on top of main. So main's just waiting for the answer. And now we come to sum numbers of 5. So this here is the label of the method that just opened up, just like main was the label of the main method. So we've opened up this method, sum numbers of 5. Well, what is it going to do? It's going to return 5 plus the sum numbers of 4. So sum numbers of 4 is now called, and it opens up. And now we have 3 methods open up on this stack of methods, and they're all waiting on the answer. Sum numbers of 4 is going to return 4 plus sum numbers of 3. Sum numbers of 3 is going to return 3 plus some numbers of 2. Some numbers of 2 returns 2 plus some numbers of 1. Some numbers of 1 returns 1 plus some numbers of 0. And finally, we have arrived at the terminating condition. Some numbers of 0 returns 0. And it's going to return 0 to where it was called from. Where was some numbers of 0? This is the method, some numbers of 0. Where was it called from? It was called from right here. So 0 is going to get returned right there. And this some numbers of 0 right here will become 0. So now some numbers of 1 is going to return 1 plus 0, which is just 1, which is going to get returned right here where it got called from. So now we have return 2 plus 1, which is 3. Some numbers of 2 is 3, of course. That's going to get returned where it got called from. So here we had return 3 plus some numbers of 2, but we just calculated that some numbers of 2 is 3. It's getting returned. So this will return 3 plus 3, which is 6. It gets returned up, and we get return 4 plus that 6 is 10. And then finally, some numbers of 5 is returning 5 plus the sum numbers of 4, which just got calculated and returned as 10. So 5 plus 10 is 15, and we return our answer to main. We save it in that variable result, and we print it out to the console. Drawing the box is a hugely important skill to be able to trace through our recursion. What's the recap, again, of this recursive strategy? Given that original problem, restate it in such a way that some example large problem is clearly articulated. Just pick some fake large number. Step 2, find a smaller version of this problem. Take a guess. Step 3, check to see if that guess is part of the answer to the original large problem. If so, we have derived our recursive idea. Step 4, terminating condition. Step 5, code her up. Another example using this construct. We want a method that's going to calculate the power of some base to an exponent, some base raised to some exponent. So if the base was 2 and the power was 4, we want to really have a method that's going to calculate 2 raised to the 4th power is 16. Once again, important to mention for clarity that you would never use recursion to solve this problem. Frankly, you would never use iteration to solve this problem. You would just type math.pow and you would calculate it, right? But again, the purpose here is to practice recursion on things that are easily understandable so we can get very comfortable and very strong with our ability to really leverage this recursive strategy that we've covered now multiple times. And then when we get to larger, more challenging problems that almost require recursion, it will be second nature for us. So the catch, we can't use the built-in POW method. We're also not going to use iteration. We want to practice our recursion. So implementing this recursive strategy once again. Let's see this example, 2 to the 4 is 16. What are we really doing when we're using this 2 to the 4th example? How are we really calculating this? How do we get 16? You could say mathematically that we're really multiplying that base 2, we're multiplying it 4 times. You're like, okay, does that help me? I don't know. And then maybe a light goes off and you realize, oh, wait, 2 to the 5 would be 5 times, 2 to the 4, 3 times, 2 to the 3, 2 to the 4th, 4 times, 2 to the 3, 3 times. And you're like, is that helpful? So that 4 is that exponent. So what's step 1 of the recursive strategy? Restate the problem that we see the large problem. Well, here's the large problem, is just multiply 2 4 times. Multiply that given base 4 times. What's step 2? Pick a candidate smaller version of the problem. We might say, well, a smaller version, instead of multiplying 2 4 times, how about multiply 2 3 times? Is that a smaller version? Yes, it is. So now let's check. Is this smaller version part of the answer to the original? And the answer is yes, it is. Here's the example. 2 to the 4, we already see it's 2 times 2 times 2 times 2. But we can also say that 2 to the 4 is really 2 times 2 to the 3. Well, guess what? That's now recursive because this is a mathematical equation and the right side of the equation is written in terms of the left side of that equation. So we just saw how we're using the smaller version, 2 to the 3, as part of the answer to the original, and we just derived the problem recursively. So using b and e as input, here's that method, pow of be, and we're going to say it's really equal to b raised to that exponent. So more generally, we can say that the pow of be, it really equals b times b to the e minus 1. This is the overall idea. Does it look recursive? It absolutely does, because the right side is in fact a subproblem of the original. So I want to come over here to the tab and I want to write that one down. We have pow of be, pow of b comma e, and we said that that equals b to the e, right? Well, and then we also said that ultimately that equals b times b to the e minus 1. That might be confusing, so let's put in some numbers. Pow of, we had 2, how about 2 to the 8? That really equals, we're trying to calculate 2 to the 8th power. So now we're going to say that that's really 2, which is our base, times 2 to the 7. Hopefully that's clear. But now let's keep it in this almost function form where I have pow of b to the e, or pow of 2 comma 8. So I want to change the color here. And so pow of 2 comma 8, it really equals 2 times the pow of 2 comma 7. There's your recursive formula. The pow of 2 comma 8, it really equals 2 times pow of 2, 7. Well, what is pow of 2, 7? It's 2 raised to that 7th power. And this is the idea. We have this now defined for us recursively. Step 4, determining, that's fantastic. Determine, that is some big brain. Determinating, I'm just going to roll with it. Determining the terminating condition. We know that the pow of some base raised up to 0 is 1. You could say a base raised to 1 is the base, right? 5 raised to the 1 power is 5. But a smaller base case would be 5 raised to the 0. So let's use that one. So we're going to use when e is 0, that will be our terminating condition. So now let's look at our full recursive formula. We have some power, the power method of some base raised to the e power is b times that same method, that base to the power of e minus 1, as long as e is greater than 0. Otherwise, this method of power b comma e, it equals 1 when e is 0. And so once again, this was the hard part. Once you have this code, well, I called that code because it basically is code. Once you have this recursive definition written like this, the code is straightforward. We're going to say if e is 0, return 1, else return b times the pow of b comma e minus 1. It's super, super straightforward once you have that recursive definition. So here's the power method of b to some exponent. If e is 0, return 1. Else, what is the power of some b to some e? We just said it's that method. It's b times the power of b to e minus 1. Well, that's it right there. Super gorgeous code, super straightforward. Let's trace through this one as well so we can see this practice of drawing these boxes to see that recursive trace. So here we have our main. We're calling the power of 2 comma 5. So here's the method label, power of 2, 5. It's going to return 2 times the power of 2, 4. Power of 2, 4 is called. It returns 2 times the power of 2, 3. Power of 2, 3 returns 2 times the power of 2, 2. This returns 2 times the power of 2, 1. This returns 2 times the power of 2, 0. And finally, we have arrived at the terminating condition, which is when e is 0. So this final recursive call is we're calling this recursive method power with these parameters 2 and 0, 2 raised to that 0 power, which is of course simply going to return 1. and we're going to return that 1 back to where it got called from, right there. So power of 2 zeros is 1. So therefore, this entire method is going to be returning 2 times 1, which is 2. And now, and of course 2 to the first power is 2, right? Now we're trying to calculate power of 2 to the 2, power of 2 squared. Well, that's going to be 4. Well, how do we get that? Return 2 times the power of 2, 1, and we just returned that answer as 4. And now we have power of 2, 3 is 2 times the power of 2, 2. That answer is now 4. So we get, which is 8. And then we have power of 2, 4 is 2 times the power of 2 to the 3. We just returned that answer, which is 8. So now we have returned 2 times 8, which is 16. 16 goes up, and we have power of 2 to the 5 is 2 times 16, and we return our answer to main. So we've now done 2 problems using this strategy, getting this recursive thinking, coding it up, and then drawing the boxes. More practice is coming, but first our interlude. We have all felt this one when you read some incredibly horrible code and you think, what moron wrote this code? But then it becomes clear that the moron was simply me. I've done that, and we have probably all done that. Let's get to some more practice. Recursion, our first practice problem. Write a method, certainly recursive, that takes in 2 non-negative integer parameters and simply produces the product of these parameters. But we cannot use multiplication to get our answer. So if the parameters are 6 and 4, your method should return 24. Of course, you would never use recursion for this. You would never use iteration. You would simply multiply those parameters and return your answer. We're trying to practice recursion, right? You've heard that spiel multiple times. So here, how would we make this happen? If we given these 2 parameters, 6 and 4, and we want to come up with 24, but we can't use multiplication, how do we do this? What's another way of saying 6 times 4? Well, we are really adding 6 4 times. That's what's going on. We're really adding 6 4 times. And so now I say, let's go think of our method. Next slide, I'm just showing you the solution. So before doing that, how about we briefly come over here to the tab. And so if I have this particular method, let's say m for multiply of 6 comma 4, which we said is going to be 6 plus 6 plus 6 plus 6. That's the large problem. What's the smaller version? Well, you could say multiply 6 times 3 is a smaller version. So 6 plus 6 plus 6. Is that smaller version, those 3 6s, are those 3 6s part of the answer to the original? Yuppers. So then you could say, well, I think maybe I can rewrite my original multiply of 6 comma 4 to be 6 plus multiply of 6 comma 3. Because this right here is really 6 plus 6 plus 6, which is this part. And so now guess what? We have written this recursively because the right side of this equation is written in terms of the left, and it is a smaller version. So that's really the recursive idea right there. We're done. What do we need now? When we've confirmed, that was step 3, we confirmed that it's a smaller version. What is now step 4? Step 4 is simply to have our terminating condition. And, before we even get to the terminating condition, let's write this more generally. What would be the general statement here? Maybe multiply of a comma b. It equals a plus the multiply of a comma b minus 1. I hope that's okay, because here's our a, here's our b. This is a, this is a, and this is b minus 1. So now that we have that done, what would be our terminating condition here? You could say, well, once b gets down to 0, so if you said if b was 0, a times 0 would be 0, so return 0. So you could say multiply of a comma 0 is 0. And that would work as a terminating condition, but check it out. What if we simply had multiply of, let's say 0 comma 10? How would we solve this recursively? It would be silly, but it would be 0 plus multiply of 0, 9, which would be 0 plus multiply of 0, 8. So we'd be adding all of these zeros together, and we'd be going through 10 recursive steps to ultimately get an answer of 0, because 0 times 10 is 0. And then you might think, wait, okay, I can get a better base case. The base case is really if either A or B is 0, then let's return 0. Otherwise, we want to return this right here. So let's go over and look at our code right now and jump right into it. So here is our solution. Multiply A comma B. If A is 0 or if B is 0, return 0. Otherwise, return A plus multiply of A comma B minus 1. Super gorgeous code directly from the recursive definition. Second problem, write a recursive method that will take in a string as a parameter and returns the number of x characters in that string. Now this is going to be funky, this next one and the one afterwards, because now we're going to be using strings and it's a little bit different at first. We can't use loops as always, only recursion. Let's look at some samples so we can make sure we understand what's going on. So here we have this method count x. It's given a string parameter, and this particular string we can see has 4 x's, so the final answer should be 4. The next example had 3 x's, it should return 3. What if there are no x's? It should return 0. So let's first really focus on this recursive strategy. How can we make that happen here? Restate the problem such that the large problem is clear. And I'm not going to even jump to the next part. I want to think about that because I want you to pause and think, man, how would I actually restate this? I'm trying to count the number of x's on a string. What is the large problem? Because if you can restate that large problem, the rest will be easier. But what is that large problem here? So what it will be is check out the following. Find the number of x's in a string of size, let's say 10. That's the large problem. What's a smaller version? Find the number of x's in a string of size 9. You're like, oh, okay. Now, if you can make it a smaller version of that same string, then that would be a smaller version. So step 3, guess or confirm that your guess is in fact a sub-problem of the original. So check out, here's that one of those samples. We had x, x, h, I, x, x. And this is the smaller version, x, h, I, x, x. And so we can see we already removed this first character of the string, which happened to be an x. So that's why I'm putting a 1 right here. Like if this first character was a w, I would have said 0 plus the count x of the remaining characters. But since this first character was an x, I said, you know what? We found an x, so return 1 plus the count x of the remaining characters. What about this one? Count x of fox would be 0 plus the count x of ox. So it is a smaller version and it works. What's the terminating condition? Count the number of x's on a string of size 10, on a string of size 9, 8, 7, 6. What's the terminating condition? Count the number of x's on an empty string. With that empty string, we will not have any x's, right? So when it's an empty string, that's your terminating condition. And let's now code this one up together. Come over here to our NetBeans. This is that same example we had previously where we have this entire recursion menu. I merely edited it and I added these 2 problems that we're now going to do together. And so this is count x, and here we are. So what is our recursive definition? This is what we really want to see and we want to practice. So if I come back here, what did we show? We said that count x of some string is going to equal 1 or 0 plus the count x of some substring, and then the terminating condition is if the string is empty. So if, let's do this. Let's start it with that. So if s is empty, So if s.length is 0, return 0. We have no x's. Else, what do we need to do? We need to look at the first character of s and check, is it an x? So I'm going to say if s.char at index 0, if it is an x, that means we found one. So return 1 plus, now we need to call this method recursively, and we need to send over what? Well, here was that string, and remember, we just saw that the first character is an x, so we want to call that method recursively with the rest of the string. So that's just going to be s.substring of 1. That's it. And now we have our else. What is this else here? This else is, let me put in some comments. This would be if the first character is an x, call the method recursively with substring 1. We found one. Else, if it's not an x, is not an x, call the method again recursively with substring of 1, but this time we did not find 1, so I'm going to type return 0 plus count x substring or s.substring 1. That's your code. Now, do I need to type return 0 plus? Is that really necessary? No, it is absolutely not necessary. It just, do I have something here on the stream deck? I'm going to put sorry, not sorry. The 0 is absolutely unnecessary. Obviously, it's not changing the result. It just feels good. It feels good to put the 0 plus for me. You don't have to. You could erase it. But I like the 0 plus because I feel that it matches with what I have up here above. That's your method. Do we want to run it and check it? Let's see. Let me scroll up some. And this was choice number 8. Enter a string. How about XXHI, small x's, XX, A, B, C, X, G, or H, X, I, X. That's 5 x's, I think. And what do we have? The number of x's in this is 5. Let's run it again. How about we just type in A, B, C, X? The number of x's is 1. Perfect. How about we try again? And let's just enter a string with no x's. And here, the number of x's in ABC is 0. Super cool. That is how we apply this recursive strategy. One more problem. Write a recursive method that takes in a string as a parameter, and it recursively computes a new string, where all of the adjacent characters are now separated by an asterisk. So here, look at the samples to make sure we understand this one. We have all star is the name of this method, followed we have now this parameter, hello. It should return a new string, as you see here, where every single pair of adjacent characters has this asterisk between them. All star of ABC would be this, all star of AB would be that. So problem solving phase before we code it. What is the process here? The strategy. Restate the problem. Once again, we're like, well, I'm a bit confused. How do I restate this problem in such a way that the large problem is clear? What is the large problem here? So some of these, it's not as clear as if I say some numbers of 8. That's the large problem. What's the smaller version? Some numbers of 7, right? That's super clear. This one, what's the large problem? Well, think back to this one we just did, count x. What was the large problem? It was count the number of x's on a string of size 10. Count the number of x's on a string of size 8. So using that same idea, what could we do here? We could say, make this new string with asterisks between every consecutive pair of characters, make this new string, or do the thing on a string of size 10. Do the thing on a string of size 9. Do the thing on a string of size 8, right? So place asterisks between adjacent characters in a string of size 10. What's a smaller version? Do the thing by placing these asterisks between adjacent characters on a string of size 9. That's a smaller version, right? Confirm that that guess is a subproblem of the original. So here, all star of ABC, we could say, well, what's the smaller version? All star of BC. Yeah, okay. Like place asterisks between all adjacent characters on a string of size 3. Well, here's a smaller version, a string of size 2. But what has to come first? I need to concatenate to this recursive call, which is going to be weird. It's the first time we've seen that. Concatenate to that recursive call A followed by an asterisk, which is going to be weird. Or what about this one? All star of Fox is going to be take F with an asterisk and then concatenate to that all star of Ox. What's the terminating condition? You might say put asterisks between a string of size 2 or size 0. Well, really, you can't place an asterisk between only one character, right? So you have to have at least 2 characters. So if the length of the string is 1 or less than 1, we are done. And so now we're ready to try to code this one up. Let's come back over here to NetBeans and let's see what we have. So here's all star. And so let's see, we say if s.length is equal to 0 or if it's equal to 1. So I'm going to say if it's less than or equal to 1, return just s. So if s was just the empty string, return empty string. If s was a single character with the character w, return w, right? Return s. Else, what do we want to return? We want to return something, whatever something is, something, plus we want to call this method recursively, all star. We want to call it recursively. And what do we want to send in here? Well, we had ABC, now we have BC. It's going to be just what we typed before. S dot substring of 1 is what we're going to send over recursively. And what are we putting here? Well, just look. We need to get that first character. We need to concatenate to it an asterisk, and then we concatenate to it the recursive call. So this is going to be s dot char at index 0 plus, we're going to concatenate to that a single asterisk, and then we concatenate to that the recursive call. That's it. Let's check it out. 9. Enter a string, ABC. What do we get? A star, B star, C star. Let's do it again. Let's enter another string. How about just A? What do we get? We got a new string with just A. Let's do it one more time. Let's do 9, and let's type in Java. And there we go. Simple. That's clear. We've now done 5 new problems. We've traced through some of them. It's a lot of fun. We need practice. Is it enchanting? Maybe. Our demotivator, collaborate. So the best of us will have to carry the rest of us. It is horrible. As always, reach out if you need anything, have any questions, leave a comment. Take care, everyone.